Hello and welcome. In this presentation, I'll be going over process fundamentals, some key ideas about processes and how their performance is measured. We'll start with cycle time, which is defined as average time between completion of successive units. So if we take a process A, which makes some output, some activity that we are performing here using inputs, and this activity is generating outputs. And if we were to stand at this spot where the outputs are being made and we count the outputs or the time between successive outputs. So the first output came out at, let's say, 10 a.m. Then the second output came out at 10:02, 2 minutes later. So this time between two successive units, once this process has reached steady state, so once it has been started and has been operational for some time, then there is a steady state cycle time, which is the time between two consecutive outputs that are being generated by this process. So that average time between completion of successive units is referred to as cycle time. Now, it's important to notice that we are talking about steady state situations. So it's not about the time when you really started this entire operation in the beginning, uh, in the morning for the first time, but once that entire process stabilizes and it is being producing products for some time, after that, you need to check what is the time between two consecutive items that are coming out. So if you were to wait a little longer and the third product also comes out, let's say at 10:04. So it's essentially between every consecutive outputs, you have 2 minutes. But we are talking about average time between completion of successive units. So sometimes you could have slightly more than 2 minutes, sometimes less than 2 minutes, but what is on average within a given period of time, the time that it takes for the completion of successive units from a given process. So that is the cycle time. Bottleneck is the factor which limits production. So if you have, let's say, a process A which feeds into process B, so you take inputs, go through process A, then process B, and finally outputs are being generated. Now, bottleneck would be the process which will be the slowest of all. So in this case, A and B, only two processes exist. Let's say we have B, which is the slower process than process A. So the slower process will be the bottleneck, which will in turn limit the production. So the overall outputs that will be generated through the sequence of steps will be determined by how fast B is, how fast the slowest process within the set of processes is. Idle time, it's the time when useful work is not being performed by a worker or machine. So sometimes, for example, if we take this situation that we had in the previous example, A and B, where B is slower than A and therefore is a bottleneck. So what will happen is that once inputs are being processed by A, you will get outputs being generated and they'll start getting clogged in front of B. So they will start waiting to be processed by B, but B is slow. So after some time, A will have produced enough work in process inventory, which lies in front of B. And hence, this machine, if it produces anything more than that, it is not really generating any useful work. So sometimes you would make this particular machine not work until the set of backlogs that exist in front of B are getting processed by B. So the time when some process or some worker or machine is not doing anything, it could be sometimes on purpose that companies could do, and sometimes it could be because of inefficiencies that you could have idle times, and that is something which is part of the understanding of how processes are performing and how they should be performing well. The capacity of a process is the measure of how much can be produced or serviced in a specified period of time. So if we have a certain task to be performed, let's say a process A, we are producing output, then the question is how many outputs are being produced per unit of time, and it'll depend on the rate at which A can actually perform its tasks. So it comes back to the idea of cycle time. So the idea of capacity and cycle time are closely related. So capacity and cycle time are related, which we will see later as we go further in this presentation. Now, capacity utilization is the measure of how much output was actually achieved relative to capacity. So many times you have a certain capacity that exists, but you are not able to utilize that entire capacity for numerous reasons. And the question is, what is the capacity utilization that you have, which is how much output you produced vis-a-vis how much you could have produced. So it's the ratio of the two. So you would have organizations running at capacity 100%, sometimes below capacity 80%. And at times, organizations wanted to have a certain level which is below 100%, so that there is some buffer capacity if needed. So capacity utilization could be a strategic variable for many companies. The idea of balance and imbalance, if every step in a process had the same cycle time, which means the average time between units coming out of different steps is exactly the same, then the process would be considered to be in balance. So we took this example of A and B. In our example, we had considered B to be the slower of the two processes. So hence B would have created products at a much slower rate, which means the cycle time here would have been longer. Two consecutive outputs coming out of B would have been much longer in duration than two consecutive outputs coming out of A. But if we were to achieve a situation where this consecutive time between two products coming out of A and the two consecutive products coming out of B are more or less very close to each other, identical in some sense, same numbers here, then we are talking about a balanced system or balanced set of processes. And that's something which has some advantage in how you would manage a given set of process or operation. Throughput time refers to the length of time spent in the process. So how much time a particular product or inventory is in the process when it has to be completed. It could include setup time, the actual time when something is being done on the process, and then if there's any wait time, that would also be part of it. So something which comes in as input, coming out as output, the length of time which it takes for that input to get converted into output and then sold to the customers. Work in process is the number of units in the process at any point in time. So this example that we had looked at earlier, where A is feeding into B, where B is the bottleneck, which means this is the slower of the two processes, would result in some work in process inventory getting accumulated in front of B by virtue of it being slower. So that would be an example of work in process inventory that exist in many companies in supply chains. Batch size, the number of units of a particular product type that will be produced before beginning production of another product type. So many organizations are making products in certain batch sizes because of economies of scale. So that particular batch size seem to be the economic order quantity for them. And hence, every time a machine is run, they need to run a batch size of, let's say, 50 units of a particular product, or 100 units of a particular product, depending on what their calculations have indicated. So that would be the batch size of a given process. Setup time, it refers to the time spent in arranging tools, changing dies, setting machine speeds, cleaning equipment, etc., in preparation for the beginning of work on a specific type of products. Now, setup times can be very long for many companies. I've known companies where there are machines that take about 8 hours to set up. So almost one shift is taken away from the organization's overall capacity just to set up the machine. So it's very important to ensure that you're sequencing the items or products in a proper way. There are organizations who have worked on their setup time and have reduced them to a substantially lower number so that most of the time is used productively. Toyota is a classic example where their stamping machines used to have very high setup times, and they have brought it down to substantially low numbers. So now the stamping machines don't take that much of setup time. Runtime is the time when there's something actually being done on a particular process or item is being processed, independent of the time required to set up the equipment. So this is the productive time, the value added time, as something which needs to be kept in mind, as in how the process is being working, how much time is being spent manufacturing an item or performing a service. And finally, Little's law. This is a law which actually allows a company to get a quick estimate of how much inventory might be existing in the overall process or set of processes that they have within the organization. So it's something which is coming out of science, physics, where there was a law which relates to something which is of a physical unit, a physical quantity, but a translation of that within the supply chain context is that one can estimate average inventory that exists in a system by looking at what the average flow rate within the system is. And this average flow rate is basically the capacity per hour or per unit of time for a given company. So per unit time, if you know what the capacity per unit time for a given company is, and what the average flow time is, in other words, what exactly the manufacturing lead time for a given company is. So we will see an example later which will illustrate how we can determine how much on average inventory might be there in a given setup with a given flow rate, which is capacity per unit time, and a flow time, which closely relates to the manufacturing lead time. So let's say manufacturing lead time here. So we can determine or estimate approximately the inventory that exists instead of counting exactly how much inventory exists every point in time. We have a way to estimate it, and it has been theoretically as well as practically shown to be quite close to what many organizations might find. So we'll take an example and we'll go over some calculations to really understand some of these fundamental aspects of processes. We'll take an example of a bakery that makes croissants, and the process is where you have raw material that gets mixed, proofed, rolled, and cut, and then work in process dough is being created. There's a parallel process of filling, which creates the filling for that croissant. The mix of the filling, work in process of filling is maintained, and the two work in process then come together. So you have this point at which the dough and the filling come together, which is then filled and folded in the form of a croissant, baked, packed, and then the finished goods are there. Now, for each of these individual activities or processes, we have a certain cycle time. So CT stands for cycle time. Right? So we have a certain cycle time for each of these different processes. So in other words, for mixed operation, 5 minutes per 50 croissants. So it's a batch size of 50. As you can see, everything is in batch sizes of 50. So whenever you're running this side or any of these operations, it has to be running at a batch with a batch size of 50 croissants. So every 50 batch size of 50 croissants come out from this mixing operation after 5 minutes. So if you were to wait at this point in time, at this place within the setup, you'll see that the first batch after steady state has been achieved will be, the second batch will come after 5 minutes of the first batch that you might have been recording. For proof operation that you have here or process that you have here is 15 minutes for every 50 croissants. So it takes a little longer in terms of the activity here. The rolling and cutting operation takes 5 minutes per 50 croissants. For mix filling, it's 10 minutes for every 50 croissants. So that's the cycle time calculation or values that have been provided to us. Once the dough is available and the filling is available, the fill and fold operation takes 5 minutes for every 50 croissants. The bake operation takes 20 minutes for every 50 croissants, so it takes the longest time here. And then packing takes about 10 minutes for every 50 croissants. So we have understanding of cycle time for every step or every process within this bigger setting that we have for the bakery. Using this situation, we will calculate some of these process measures and understand what that means. So the first question will be, which we want to understand, is what is the cycle time of the process of preparing the dough and mixing the filling? So we have two parallel things going on. We are preparing the dough at the top, and then we are preparing the filling at the bottom. So this first calculation we are doing is for the cycle time for the process of preparing the dough. And what we need to look at is what is the longest time for dough preparation among all the processes that we have. Which process has the longest time that we can see among the cycle time? So we see that the 15 minute per 15 for every 50 croissants, which is in the proofing operation, is the longest time that we have in that series of steps that we take to make the work in process dough. So therefore, the longest process time dictates the cycle time for this entire set of series of activities that we do. So it doesn't matter what these other ones are. Really, what matters is the longest time. So our cycle time for the process of preparing the dough is 15 minutes for every 50 croissants. Likewise, if we look at the raw material filling and finally work in process filling operation, there's only one activity that has to be done, which is mixing. And that requires 10 minutes. So for that, it's a straightforward cycle time of 10 minutes per croissant. So all we have to look for is if there are series of processes, the one which takes the longest time will be the cycle time for the entire process or entire sub process that we have here. Right? So we choose uh, the 15 minutes for the first sub process, which is that of work in process dough, and 10 minutes for the second sub process, which is that of making the raw material filling. Between the two, if we were to stand at this point in time where the two work in process inventories of dough and filling have to come together and try to understand what is the combined cycle time here. So cycle time at this point in time, it will be the longer of the two numbers. So we have 15 and 10 minutes every 50 croissants. So the two dependent parallel processes, because both of them have to finish before filling and folding operation can begin. And hence the cycle time of this combined two activities of work in process dough and work in process filling will be the longer of the two numbers, bigger of the two numbers, which is 15 minutes for every 50 croissants. So that's the cycle time for the two dependent. This is called dependent parallel processes because they depend on each other for the next activity, which is filling and folding to accomplish. Next is what is the cycle time of the overall process? So now we are interested in the entire bakery operation, not just the two parallel processes, but including the fill and fold, bake, and everything. So what is the cycle time of the entire process? Once again, we now know for this entire two parallel dependent processes what exactly their cycle time was, which was 15 minutes for every 50 croissants. We just calculated that. Now we go forward with that and then look for the serial set of processes. What is the longest time we are taking for any given process, which is this baking step of 20 minutes for every 50 croissants. So the longest process time for the remaining set of processes is 20 minutes for 50 croissants. Now, the cycle time for the overall process, if we consider this entire bakery here, will be essentially the longer of 15 and 20, whichever is the longest. So this parallel process had 15, and then we had the serial process, which has 20. So it's the 20 minutes for every 50 croissants that become the cycle time for the entire bakery. So if someone was to stand at this finished goods warehouse and examine the rate at which these croissants are coming into the finished goods inventory, the time between two consecutive croissants will be 20 minutes after you reach the steady state. So that 20 minutes become the cycle time for this bakery operation. Next is what is the manufacturing lead time? Now for the manufacturing lead time, we first look at these dependent parallel processes. And to understand what the manufacturing lead time is, we take these two parallel operations And we'll consider the longer flow between the two parallel processes. So the first flow, which is the top one, now we're looking at the manufacturing lead time, not the cycle time. So we will add individually each of these process times. So 5 times 15 plus 5 gives us 25 minutes for every 50 croissants. The bottom set of steps that we have here only has one activity that we are performing, which is mixing, and that takes 10 minutes per 50 croissants. So the longer of these two is the one which we will take here, which is the longer flow, and that happens to be 25 minutes. So the first dependent parallel steps that we have together will give us this 25 minutes for every 50 croissants that we have calculated for the first half in some sense. And then looking at the second half, which is a set of serial processes of filling and folding, baking and packing. Here, what we will do is they have to be done one after the other. So we add 5 times 20 times 10, giving us 35 minutes. So this is 35 minutes. So we have 35 minutes for this series of processes and 25 minutes from the previous dependent parallel processes. So overall, the total manufacturing lead time when we combine everything will be the sum of 25 minutes plus 35 minutes for every 50 croissants, which is 60 minutes or 1 hour. So that's the manufacturing lead time for this bakery. Next question is, what is the bakery's overall daily capacity of croissants? Assume that the bakery operates the oven 8 hours a day. Now, to understand the overall daily capacity of croissants, remember that I mentioned that capacity and cycle time are related to each other. We already know from the cycle time calculations that for this entire bakery, every successive batch of 50 croissants will come out in 20 minutes. A successive time between two successive batches will be 20 minutes. So 20 minutes, when we convert that into hours, will be 20 divided by 60, which is 1/3 of an hour, right? So 1/3 of an hour for one batch. So if we have 8-hour operation, right, in 8 hours, we can produce how many batches? We will be able to produce 1 divided by 1/3 multiplied by 8. So this is the basic algebra that we've learned a long time ago. And this gives us 24 batches that can be produced in this 8-hour duration that we have, which if we translate into number of croissants, which is what we want to answer here. So 24 times 50 croissants in every batch gives us 1200 croissants as the total number of croissants that the bakery can produce in every 8 hours. Now, the last, or rather the next question is, use the manufacturing lead time as the throughput time for the bakery and determine the average work-in-process inventory that you would expect in the bakery. Now remember the Little's law that we mentioned, that we have a way to estimate approximately how much inventory might be there in the system. And we're going to use that Little's law for this particular problem. We've been told that we can use the manufacturing lead time, which we already calculated, as the throughput time for the bakery. So the manufacturing lead time we calculated was 60 minutes or 1 hour, and that's going to be used as the throughput time. That throughput time is essentially the average flow time for the process. So whatever the total time it takes for a product to go into the system and come out of the system, that would be the average flow time for the given process for this bakery, which is 60 minutes or 1 hour. The average flow rate, as I mentioned earlier also, is the capacity per hour. We now have an idea of the cycle time, and cycle time is connected to the capacity of a system. The cycle time gave us the understanding that every 50 croissants can be made in 20 minutes or 1/3 of an hour. Hence, the capacity per hour, which is what we're interested in, will be 50 times 3. So every hour, we can make 150 croissants or 3 batches of 50 croissants, right? So that's the capacity per hour that we have. So now we have the required information to use Little's law, which is to find average inventory. In our case, we are interested in work in process inventory. we need the average flow rate and average flow time. So the flow rate is 3 batches per hour. That's what we have here, 3 batches of 50 croissants every hour, multiplied by 1 hour, which is our average flow time, 1 hour. Everything has to be in the same unit. So if we are using hours as our fundamental unit here for capacity or average flow rate, so we need to make sure that we're using also this hour here. So 3 batches per hour multiplied by 1 hour gives us 3 batches of croissants. So 150 croissants is what we would expect to see as work in process inventory at a given point in time within the bakery. So that's the calculation for understanding approximately what the work in process inventory will be. So this presentation, we got to understand some of the fundamental aspects of processes. We also understood how we can understand how the process is doing, how to understand the capacity of the process, what cycle time is, and how we can use information on cycle time, manufacturing lead time, and other things to determine what might be the average inventory that might be lying in the system. Thank you.